Everything is in balance. Well, not really. Life is messy, if only because our Mother Nature and her world are forever more complex than we realize. But, after 13 billion years of cosmic evolution, 4.5 of which included the evolution of our planet itself, things are allowed to settle down, to rest. It is rare that anything happens abruptly on a timescale befitting nature, not human. Consequently, the systems we find ourselves in are languid, even though they're ever moving. They tend to change over the course of tens of thousands, hundreds of thousands, millions, tens of millions, hundreds of millions of years. Think of the tectonic plates, or the biosphere, or evolution, or climate, or local geography inversely. We, humans, we're alive at a glorious time, and it is glorious indeed because it is a time we get to witness. But the past that seems so inaccessible always fascinates us. So we've tinkered and we've toiled, and we've built some of the greatest machinery and the most robust computers just to get a glimpse of what was before us. It is a little funny, and so terrifyingly ironic, that so many of us are too scared of what may happen after us, that they refuse to look at all. Based on the annual analysis from NOAA's Global Monitoring Lab, global average atmospheric carbon dioxide was 422.8 parts per million, ppm for short, in 2024, a new record high. The increase during 2024 was 3.75 parts per million, the largest one-year increase on record. In 1958, at Mauna Loa, the mole fraction of atmospheric CO2 was 315.34 parts per million. This is a direct measurement. In the year 2000, it was 369.7. 2 decades later, in 2020, the recording was 414.21. Just 4 years after that, in 2024, 424.61. It is abundantly clear that something is happening. Thus far in our endeavor, we haven't said what, but something, however mundane, however special, however worrying, however whatever, is happening to produce these exponentially rising measurements. One possible explanation is merely that the measuring devices are scuffed in some way. So, how do they do it? Fortunately, the team at Mauna Loa have provided us with this exact information. Here is a very brief summary. Since 2019, they have used cavity ring-down spectroscopy. A laser is fired between two mirrors in a chamber of air and then turned off, whereupon the light energy decays. The rate of decay can be measured, and the difference in rates between when the laser emits a wavelength that CO2 absorbs and a wavelength that it doesn't tells us the concentration of CO2. Concentration, though, is not mole fraction, and they want mole fraction because it is the most useful measurement for studying the removal and adding of gases to the atmosphere. So there is some math involved in figuring that out, but importantly right now, they also have to do frequent calibrations to make sure every variable in the formula is tightly controlled. To calibrate, gas with already known mole concentrations of CO2 are run through and analyzed, and then more math is done to ensure proper readings. This is done every 2 weeks. And these measurements are consistently and repeatedly compared to other gases and other laboratories, often using completely different methods, and the measurements are almost always within 0.2 parts per million of each other. Before 2019, the laboratory used a different process, measuring the total absorption of infrared rather than the rate of absorption. However, the calibration was the same, the math was for the same purpose, and the comparison to other measurements still returned a consistency better than 0.2 parts per million. Now, I will be sharing the entire paper, because it is all incredibly useful and good information, and it would behoove you to learn the science behind the measurement. If you believe the methods they use are reliable, and you aren't too interested in the details, you should skip to the next section. However, if you are unconvinced of their veracity by my poor summarization, Here's how we know with extreme confidence that these measurements are accurate. I hope you're comfortable, because this is going to be a long read. Summary. We have confidence that the CO2 measurements made at Mauna Loa Observatory reflect truth about our global atmosphere. The main reasons for that confidence are: 1. The observatory near the summit of Mauna Loa, at an altitude of 3,400 meters, is well situated to measure air masses that are representative of very large areas. 2. All of the measurements are rigorously and very frequently calibrated. 3. Ongoing comparisons of independent measurements at the same site allow an estimate of the accuracy, which is generally better than 0.2 parts per million. Mole fraction in dry air. What do we need to measure? Most people assume that we measure the concentration of CO2 in air, and in communicating with the general public, we frequently use that word because it is familiar. The quantity we actually determine is accurately described by the chemical term mole fraction, defined as the number of carbon dioxide molecules in a given number of molecules of air after removal of water vapor. For example, 413 parts per million of CO2, abbreviated as ppm, means that in every million molecules of dry air, there are on average 413 CO2 molecules. The table below, and presumably to the side on which way editing me decides, but it's on your screen now, so you can tell which one. I don't know. Lucky you. The table below gives approximate values of gases in the atmosphere for 413 ppm of CO2 in dry air. This is roughly the average amount of CO2 in the atmosphere in the middle of the year 2020. All species have been expressed as ppm, turning 78.09% nitrogen into 780,900 parts per million. The rightmost column shows the composition of the same air after enough water vapor has been added to make the mole fraction of water vapor in wet air 3%. Again, look at it on your screen now. That'll be the same going forward for all of the charts and graphs and other whatever you need to see. Well, I shouldn't even have to explain this because I'm also showing you the text, aren't I? Yeah, I forgot about that. Thanks, future me. Why do we express the abundance of CO2 as a mole fraction in dry air? The concentration of a gas is defined formally as the number of molecules per cubic meter. The goal of our measurements is to quantify how much CO2 has been added to or removed from the atmosphere. The concentration does not give us that information because it primarily depends on the pressure and temperature, and secondarily on how much the relative abundance of each gas has been diluted by water vapor, which is extremely variable. Only the dry mole fraction reflects the addition and removal of a gas species because its mole fraction in dry air does not change when the air expands upon heating or upon ascending to higher altitude where the pressure is lower. Nor does it change when water evaporates or condenses into droplets. Why is this so important? Here is an example. The amount of CO2 is higher in the northern than in the southern hemisphere as a result of the combustion of coal, oil, and natural gas. The measurement of this difference gives us crucial quantitative information about the emissions and removals of CO2. The concentration change produced by the addition of water vapor can be greater than the CO2 difference between the two hemispheres. In contrast, the difference in dry mole fraction does reflect the differences in emissions and removals between the hemispheres. One often encounters in the literature the term mixing ratio. This is ambiguous. Does it apply to mass or to the numbers of molecules? In an attempt to clear that up, one also finds mixing ratio by volume, abbreviated as ppmv for CO2. However, that can still be ambiguous. Does it mean partial molar volume of CO2 relative to molar volume of whole air? That would only be correct if all the constituent gases of air behaved as ideal gases, which we know is not true. Furthermore, the calibration standards used by greenhouse gases in air are made as, and expressed as, mole fractions in dry air. All national metrology institutes, with NOAA/GML representing the WMO Global Atmosphere Watch community, participate in comparisons of reference gas standards that are called key comparisons of amount of substance ratios. The unit of amount of substance is the mole. Data availability. The CO2 data that is described on this page is available at the GML Data Finder, where data options have been filtered to show CO2 data from all of the GML observatories, in addition to Mauna Loa, Barrow, Alaska, American Samoa, and South Pole are included. Data is available as hourly, daily, and monthly averages. Measurement technique. Although we describe measurement techniques for CO2, they apply also to measurements of methane, CH4, and carbon monoxide, CO. How does the CO2 analyzer work? In April of 2019, a new CO2 analyzer was installed at Mauna Loa that uses a technique called cavity ring-down spectroscopy, CRDS. Prior to this date, an analyzer was used based on infrared absorption. CRDS is based on the measurement of the rate of absorption, rather than the magnitude of absorption, of light circulating in an optical cavity. The beam from a laser enters an optical cavity consisting of 2 or more highly reflective mirrors. The laser beam is reflected back and forth inside the cavity, the so-called ring-down cavity. The laser is then turned off and the light intensity inside the cavity steadily leaks out and decays to zero in an exponential fashion. A detector measures the intensity of the transmitted light as a function of time. The decay time is called the cavity ring-down time. By comparing the ring-down times when the laser is at a wavelength that the CO2 molecule does not absorb to the ring-down time when the laser is at a wavelength that the CO2 molecule does absorb, the amount of CO2 can be calculated. The analyzer also measures CH4 and CO. Calibration of the instrument. An important aspect of the measurements is the ongoing calibrations of the analyzer. Air flows continually through the instrument, after having first been dried in a cold trap where the water vapor freezes out as ice on the walls of the trap. Unfortunately, the absorption that we measure in the instrument does not depend on the CO2 mole fraction, but on the total amount of CO2. Therefore, we also accurately control the temperature and pressure in the instrument, as well as the flow rate, and we do frequent calibrations with reference gas mixtures of known amounts of CO2 in dry air, stored in high-pressure aluminum cylinders, spanning the expected range of the measurements. We continuously record the output from the analyzer, but we need some way to convert this output to true mole fraction values. That is, this equation on screen now, because I don't know how to vernacularly say that. The mole fraction... Hair in my mouth. Hair still in my mouth. We're good. We got it. The mole fraction amount is some function of the analyzer output. The method we use to obtain this function is to use 5 standard gases of very well-known values of CO2, with a wide range of values that span the entire range of natural ambient CO2 values. In the case of Mauna Loa, the range of the standards is from about 350 to 430 parts per million. Each of the 5 standards is compared several times with a reference gas from a tank of CO2 in dry air called R0, and the average difference between each standard and the reference gas is computed. We then plot up each of these differences, delta R0, versus the known mole fraction of CO2 in the standards, and fit a polynomial function that gives us this equation, somewhere around here. That is, the mole fraction amount of our sample is a function of the difference between the sample and the reference R0. C0, C1, and C2 are the coefficients of the polynomial function. This calibration sequence is performed approximately every 2 weeks. The calibration method allows us to determine the response of the analyzer without having to know the amount of CO2 in the reference R0, and the highly calibrated standard gases are used sparingly. Measurement method. An example of the output from the analyzer for every day is shown in Figure 1. It might be on this side of the screen, it might be on this side of the screen, I don't know yet. 2 separate intake lines are used for sampling ambient air. The intake lines are from the top of a 38-meter tall tower next to the observatory, to avoid any influence on the measurements by human activities at the observatory. Each intake line is measured for 5 minutes, alternating between line 1 and line 2. Once an hour, the reference gas R0 is measured for 5 minutes. Once per day, 2 target tanks are measured for 15 measurements each, seen in hour 6 and hour 17 in Figure 1. The first few minutes after each gas change are not used to allow time for the previous gas to be completely flushed from the analysis system. The difference of the ambient air measurements from the reference R0 are calculated, and these differences are put into equation 1 to calculate the true ambient mole fraction CO2. By making the measurements relative to the difference from R0, any short-term drifts in the analyzer are accounted for. Target gas. The calibration of the analyzer outlined above depends on accurate measurements of the standard gases. We provide for a check on the calibration response by running what we call 2 target gases, treated as having an unknown mole fraction, alternating every 11 hours through the measurement system. In reality, the mole fraction of the target gas is very accurately known. If the response of the analyzer as calculated in equation 1 is incorrect, the measurement of the target gas will produce the wrong result. By comparing the calculated values of the target gases with their known calibrated CO2 values, we can detect problems with the analyzer calibration. One target gas is near the ambient levels of CO2, and the other is higher than ambient. The repeat cycle of every 11 hours causes the target measurement to slowly move through the diurnal cycle because each day it is measured 2 hours earlier than on the previous day. This helps in determining if there are any problems related to the time of day. Data selection for background air. In 1957, Dave Keeling, who was the first to make accurate measurements of CO2 in the atmosphere, chose the site high up in the slopes of the Mauna Loa volcano because he wanted to measure CO2 in air masses that would be representative of much of the northern hemisphere, and, hopefully, the globe. That goal has not changed. We still want to eliminate the influence of CO2 absorbed or emitted locally by plants and soils, or emitted locally by human activities. Dave Keeling also introduced the principle of a rigorous calibration strategy that we still employ today. The observatory is surrounded by many miles of bare lava, without any vegetation or soil. This provides an opportunity to measure background air, also called baseline air, which we define as having a CO2 mole fraction representative of an upwind fetch for hundreds of kilometers. Nearby emission or removal of CO2 typically produces sharp fluctuations in space and time in mole fraction. These fluctuations get smoothed out with time and distance through turbulent mixing and wind shear. A distinguishing characteristic of background air is that CO2 changes only very gradually because the air has been mixed for days without any significant additions or removals of CO2. Another common word for emissions is sources, and for removals, sinks. Figure 2 shows an example of the data selection procedures we use to categorize air that has likely been influenced significantly by nearby sources/sinks. The plot is for 2 days, July 18 and 19, 2020. First, the time axis needs to be explained. The bottom axis of Figure 2 reflects that we keep date and time at the Mauna Loa Observatory in Universal Coordinated Time, abbreviated as UTC. UTC is the same across the entire world. It succeeded Greenwich Mean Time in 1961 and is widely used and unambiguous. Local time in Hawaii lags UTC by 10 hours, so that 10 a.m. UTC corresponds to midnight locally. The upper axis has labels indicating the local time in Hawaii. At Mauna Loa, we use the following data selection criteria. 1. The standard deviation of the 5-minute mole fraction averages should be less than 0.30 parts per million within a given hour. A standard deviation larger than 0.30 parts per million is indicated by a V flag in the hourly data file, and by the red color in Figure 2. 2. There is often a diurnal wind flow pattern in Mauna Loa driven by warming of the surface during the day and cooling during the night. During the day, warm air flows up the slope, typically reaching the observatory at 9 a.m. local time, 19 UTC, or later. The upslope air may have CO2 that has been lowered by plants removing CO2 through photosynthesis at lower elevations on the island, although the CO2 decrease arrives later than the change in wind direction, because the observatory is surrounded by miles of bare lava. Upslope winds can persist through about 7 p.m. local time, 5 UTC next day, or local hour 19 in Figure 2. Hours that are likely affected by local photosynthesis, 11 a.m. to 7 p.m. local time, 21 to 5 UTC, are indicated by a U flag in the hourly data file, and by the blue color in Figure 2. 3. In keeping with the requirement that CO2 in background air should be steady, we expect the hourly average from one hour to the next should not differ from the preceding hour by more than a small amount. Data where this hour-to-hour change exceeds 0.25 ppm is indicated by a D flag in the hourly data file, and by the color green in Figure 2. However, if there are 3 consecutive non-flagged hours that either precede or follow an hour with a D flag, then the D flag is removed. This handles a step change in CO2 concentration, where the edges of the step agree with surrounding hours, but not with the single adjacent hour. 4. After the application of the V, U, and D flags, there can be times when a single hour remains unflagged, but is bracketed by flagged data. This makes it unclear if this single hour could be representative of background air or not. We therefore apply a S flag to these single hours. Hour 6 UTC on July 19 in Figure 2 is an example of this. Similarly, a pair of hourly data could be bracketed by flagged data. As a final step, we check if there are any unflagged data within plus or minus 8 hours of an hourly average, ignoring adjacent hours. If not, then that hour is given an N flag. Hours for which we do not have valid air measurement are flagged with either a star or I character in the hourly data file. The hours during which we do a standard gas calibration are an example, but there are also other instrumental causes, such as mechanical problems with pumps and valves. The frequency for each of these flags for a typical year, 2014, is shown in Table 1. Hourly means are calculated wherever possible, and how we use that data is indicated by the selection flags. No data are thrown away. The hourly averages are calculated from the raw data, which are the analyzer output values recorded for the air measurements as well as for the reference gas mixtures used for calibration and for the target gas. On average, over the entire record, there are 9.0 retained hours per day with background CO2 mole fractions. Because of the upslope wind condition flag U, there is only a maximum of 15 hours per day of background values possible. Figure 3 shows a plot of the CO2 data for 2014 for each flag type. Even though the data selection method identifies background data properly most of the time, there can still be conditions where the applied selection flag is not appropriate. The user of the data should be aware of this and modify the selection as needed. Auxiliary measured variables. System status variables measured and continuously recorded are analyzer temperature, cold trap temperature, room temperature, sample flow rate, and both pressure and flow rate through both air intake lines from the tower. How we calibrate the reference gases. Since 1995, our laboratory has been the CO2 Central Calibration Laboratory of the World Meteorological Organization, WMO. Before 1995, that role was filled by the Scripps Institution of Oceanography of the University of California in San Diego. We maintain the WMO mole fraction scale for CO2 in air. The WMO scale is based on 15 so-called primary standards that are calibrated in terms of fundamental quantities at intervals of about 1.5 years by manometric measurements. They have CO2 mole fractions that span the range of ambient air. The primaries are stored in high-pressure aluminum cylinders. The primary standards themselves are only sparingly used, so that we can build up a calibration history of each of them over several decades. During a calibration episode, lasting 2 to 3 months, each primary is measured 3 times. Each time a sample of air is taken from the cylinder and its pressure and temperature inside a closed volume are measured very accurately, after temperature and pressure have stabilized in a temperature-controlled environment. The volume of approximately 6 liters is accurately known. Once the pressure, temperature, and volume of a gas are known, the amount of gas can be calculated, taking the temperature-dependent compressibility of the gases into account. Then the air, with the CO2 that is to be determined still in it, is slowly and completely flowed at low pressure over a cold trap cooled with liquid nitrogen. The condensate in the cold trap consists of carbon dioxide, nitrous oxide, and a residual water vapor. The latter is low, corresponding to 1 parts per million or so in the dry, high-pressure cylinder. After separation of the water vapor component, the carbon dioxide and nitrous oxide are transferred to a small volume, about 10 cc, which has also been very accurately calibrated. After stabilization, the pressure and temperature are once again recorded and total amount of the 2 remaining gases calculated. At that point, we have determined the combined mole fraction of carbon dioxide and nitrous oxide in the cylinder air. The latter typically comprises less than 1/1000th of the total, and we correct for its contribution after measuring nitrous oxide separately on a gas chromatograph. The accuracy of the WMO scale has been estimated, based on the accuracy of the temperature, volume, and pressure measurement, and the gas handling procedures, at 0.10 parts per million. It has been compared several times to calibration scales established independently by other laboratories that were based on weighing a small amount of pure carbon dioxide that was then mixed into a large, also accurately weighed amount of carbon dioxide-free air. We have also compared to the previous WMO scale maintained by Scripps. These comparisons are compatible with our internal accuracy estimate. The manometric calibrations are a very time-consuming process. While we need to calibrate thousands of cylinders, many of which are used by other laboratories around the world, we transfer or propagate the WMO scale to other high-pressure cylinders of CO2 in air in a much more efficient way by comparing them to each other on an infrared gas analyzer system. This is very similar to how we measure outside air by comparing the voltage response of unknown air to the response of air with known mole fractions. The repeatability of these transfer calibrations, done 1 week or more apart, is typically 0.01 to 0.02 parts per million in the range of ambient air. The sequence is similar to that of target gas calibrations at the field observatories where all cylinders are measured repeatedly, one after the other, with the known gases interspersed between the unknown gases. Because we want to use the primary standard sparingly, we transfer the scale twice per year through these comparisons to secondary standards, which in turn get used to calibrate all other reference gases.
These secondaries typically last for 3 to 5 years. An important aspect of the calibration strategy is that reference gas mixtures are not only calibrated before use, but also after their use when the pressure is low, but not close to zero. Reference gas mixtures are recalled for recalibration when about 20% of the air is still in the cylinder, because experience has shown that the CO2 mole fraction tends to drift more when the pressure becomes low. Because the raw data consists of voltages, it is possible to recalculate corrected mole fractions for the measured atmospheric air after it has become clear through recalibration that a particular reference gas has drifted. Fortunately, this problem greatly diminished when we made the switch from using steel cylinders to aluminum cylinders. Don't worry, we're almost done. Replication of the field measurements. We know from experience that careful calibration is necessary, but not sufficient for making accurate measurements. There are many potential biases related to gas handling, drying that are not covered through the calibration. The ultimate test of how accurate these measurements are likely to be is to compare them with other measurements, done independently with different methods and/or by different laboratories. At Mauna Loa, we have both. In Figure 4, we show a comparison with two sets of grab samples of air in glass flasks, done weekly in pairs. One set, called S, are samples taken through the intake line used by the continuous analyzer, and diverted just before entering the analyzer. The second set, called P, are completely independent from the continuous analyzer system. They are taken with a battery-operated pump, an extendable air intake mast, at a spot on the lava away from the observatory buildings. The flask samples are sent to our laboratory in Boulder, Colorado, where they are analyzed together with thousands of other air samples from all over the world. There is a fair amount of scatter in the comparisons, partly because we are comparing a spot sample, a roughly 20s average, to the longer average of the continuous analyzer when the sample was taken. On average, the P flasks differ from the continuous analyzer by 0.12 parts per million, and the S flasks by 0.08 parts per million. Important are systematic biases that persist over a good part of a year or more, portrayed by the solid smooth lines fitted to the respective datasets. One can see that most of the time the biases are less than 0.2 parts per million. We have a similar comparison with the CO2 measurements performed by the Scripps Institution of Oceanography, the program started by David Keeling. They have always maintained their own manometric calibration scale. They use a different analyzer system, and their data selection techniques for selecting background air are different from and independent of our methods. They also compare on a regular basis with their own grab samples. A comparison of the Scripps monthly mean CO2 data, obtainable from this link wherever it's on screen it is, shows that the average difference during 1974 to 2019 between the Scripps and our monthly means is 0.07 parts per million. The above comparisons give us confidence that CO2 measurements are generally accurate to better than 0.2 parts per million. Observed variance of CO2 in the atmosphere. We present two typical examples of measured CO2 mole fractions over the continent to demonstrate what an excellent choice Mauna Loa is for making background measurements. Figure 5a shows 1 week in July 1999 of CO2 measurements made on a tall TV antenna in a forested area in northern Wisconsin. Again, the time is recorded as UTC. In Wisconsin, the local time is lagging UTC by 6 hours. The measurements are made at 6 height levels on the tower, from 11 meters to 396 meters above the ground. Near the ground, there is a very large diurnal cycle which decreases with altitude. At sunset, when photosynthesis shuts down, the CO2 mole fraction shoots up, especially at the lowest levels, because plants and soils keep respiring during day and night, releasing CO2. Sunset occurs at around 1 a.m. UTC, which equals 7 p.m. local time of the previous day at the tower. During the day, photosynthesis is stronger than respiration, causing net removal of CO2 from the atmosphere, and the CO2 gradient along the height of the tower reverses. Now, the 11-meter level near the ground has the lowest CO2 mole fraction. The mole fraction differences between the levels are very small during the day because the air is vigorously mixed, typically up to altitudes of 1 to 2 kilometers. During the night, the ground cools and the atmosphere becomes stable, with little vertical mixing because the coldest, densest air is near the ground. The respired CO2 is trapped in the stable boundary layer near the ground, which may have a thickness of only tens of meters. The buildup of respiratory CO2 near the ground is more strongly dependent on the atmospheric stability, driven by the weather, than on the rate of respiration. It is more difficult to quantify emissions/removals of CO2 over the continent than at background sites like Mauna Loa that average over very large areas. Figure 5a also shows variations of CO2 on the timescale of weather systems, several days to a week, with the wind bringing air masses from different directions. Figure 5b presents 1 week in January, which portrays a typical situation in the winter. There are no strong sources/sinks of CO2 in the vicinity of the tower because we see fairly uniform mole fractions along the height of the tower. The variations on the timescale of weather systems remain due to sources/sinks far away from the tower. And would you look at that, we're done. All that to say, we are extremely confident that these measurements are accurate. Back to your regularly scheduled programming. And for me, hopefully, to bed, because it is 1 a.m. Moreover, we are very sure that these readings accurately represent large portions of the global atmosphere. But to be certain, we can look at the data from other laboratories. From the Baroatmospheric Baseline Observatory, located on the northernmost tip of Alaska, as close to the North Pole that you can get on US soil, the average of 2024 was 425.62 ppm. Compare this to its 2000 readings, for reference, of an average of 371.36. These datasets also specifically request the citation text, so that's how I'll provide it in the description alongside the link. It looks weird, but just go with it. Then from Tutuila in American Samoa, the 2024 average was 421.61 ppm, compared to their 2000 average of 368.63. And the South Pole in Antarctica. Their 2024 measured average was 420.07 ppm. In 2000, it was 367.26. All 4 locations from vast regions on Earth, all isolated as can be from the normal variations of airflow, agree on these measurements down to less than a % difference, most of which is already accounted for as explained by the Mauna Loa team, and they agree on the exponential increase. We can therefore confidently assert that this is a very real phenomenon. It is also an important phenomenon to understand thoroughly. There are 2 options: that it will affect us, or that it won't. We need to understand which it is. So we search for the cause. Given that the rest of you can't see the future, and we don't know in the present, we are left with turning back. Enter glaciers. Glaciers are cool. I mean, really cool. They're ice! And also awesome, and I love them very much. Even better is an ice sheet, which is effectively one absolutely massive glacier, like Antarctica. These sheets grow through an accumulation of snow on their surface, which then gets pressed down and compacted into solid ice by new snowfall above it. This is a process that has been occurring year after year after year since the ice sheet first formed. The large ice sheets are also very special in that they consist of massive plateaux, where snowfall is roughly even, and there is very little that can disturb the ice once formed, be it geological or the shifting of the ice itself. That was an unintentional pun given by my mispronunciation, but we're going to go with it. For this, we can study the conditions of the ice and snow from up to 800,000 years ago. More importantly than that, we can study what was in the snow at the time it fell. Dust from across the globe that make their way into the atmosphere eventually fall down, and some of that falls down on the ice sheets, or the very snowflakes form around the dust particles in the air. This dust is then buried under the snow and becomes trapped in the ice. Sometimes this dust can even be traced back to where it originated from, thanks in large part to dating methods on the ice core, which are cylinders taken from the ice. Specifically, because the snow builds in layers, and those layers are subject to seasonal changes, each layer represents a year, and like the rings of a tree, we can count them. This also and especially applies to volcanic eruptions. As just one example, in a core from Greenland, 4 ash lines were observed. Dating of the layers of the ice core exactly corroborated other sources of evidence as to the date of those eruptions. Other information that can be gleaned from the sheen of ice includes prehistoric precipitation rates in the region, depending on the thickness of each layer of the core, warmer and cooler summer temperatures, as warmer temperatures will melt more top snow, and this water then freezes and is physically distinct from the compacted snow. To be more exact about eruptions, tephra from any particular eruption will have a unique chemical signature unlike all others, and thus finding the same tephra in multiple locations demonstrates their synchronicity. Finding them in multiple ice cores clearly demarcates those sections as from the same time, allowing yet more confidence in our dating capabilities. But two sources of information are more important for our purposes here than the rest. Firstly, deuterium and 18-oxygen. Deuterium is an isotope of hydrogen that has one neutron, where normal hydrogen has none. 18O is an isotope of oxygen, with two more neutrons than usual. They are chemically identical to, but way more than, their standard counterparts. These isotopes are also stable and do not decay. Here I'll quote an article from Scientific American. Using sensitive mass spectrometers, researchers are able to measure the ratio of the isotopes of both oxygen and hydrogen in samples taken from ice cores, and compare the result with the isotopic ratio of an average ocean water standard known as SMO, Standard Mean Ocean Water. The water molecules in ice cores are always depleted in the heavier isotopes, that is, the isotopes with the larger number of neutrons, and the difference compared to the standard is expressed as either 18O or D. Both of these values tell essentially the same story, namely that there is less 18O and D during cold periods than there is in warm. Why is this? Simply put, it takes more energy to evaporate the water molecules containing a heavy isotope from the surface of the ocean. And as the moist air is transported polewards and cools, the water molecules containing heavier isotopes are preferentially lost in precipitation. Both of these processes, known as fractionation, are temperature dependent. At a range of sites in the polar region, scientists have measured a near linear relationship between 18O and D in samples of modern snowfall taken over several years and the mean annual temperature. This relationship can be used to calibrate the isotope ratio thermometer, although the calibration changes a little during ice age climates. Plotting either 18O or D with depth along the length of an ice core reveals the seasonal oscillations in temperature, and researchers can also count annual layers in order to date them. From the very deepest ice cores reaching depths of more than 3 kilometers in the Antarctic ice sheet, we can clearly see the steady pulsing of the ice ages on a period of around 100,000 years. From a site called Dome C in Antarctica, we have recently reconstructed the climate spanning the last 750,000 years, and have shown 7 ice ages, each interspersed with a warm interglacial climate such as the one we are living in today. Isn't that so cool? It's so cool. Oh my god, it's so cool. Secondly, contained within the ice core are small pockets of air. Air from when the snow first fell. We literally have a repository of ancient air that has maintained its composition for 800,000 years, and every time in between. This is our first step in divining the source of our current CO2 measurements, examining how these rates have changed in the recent past. The following graph, and hopefully I'm sidestepping enough to be able to show it in post without obscuring my beautiful handsome face here, shows CO2 measurements spanning back 1,000 years. Everything that is dark blue is with modern direct measurements as elaborated on above, and everything in lighter blue is ice core measurements. The graph of the past 400,000 years is the following. Then the past 650,000 years, and 800,000. In the past 800,000 years, there has never been a concentration of atmospheric carbon dioxide even close to our current measured level of over 420 parts per million. Roughly 350,000 years ago, the concentration reached just about 300. That is the highest the ice cores have shown us. Our current measurements, in the spans of hundreds of thousands of years, are therefore deeply abnormal. From the glacial record, this event, whatever it may be, is entirely unprecedented. This knowledge, combined with our proxy for temperature via isotope measurements, allows us to test our model proposed in Act 1, namely the relationship between temperature and CO2 levels. Our graph for 650,000 years into the past does precisely this, and the resemblance is uncanny. It's near perfect, down to changes in concentration of 20 parts per million, reflecting changes in temperature. Adding on another 150,000 years in the past returns the same result. These deep-rooted, phenomenally specific correlations are evidence of a causational relationship, and moreover, this is exactly what we predicted based on our knowledge of carbon dioxide's infrared-absorbing properties. Moreover, we are also able to measure the isotopes within the trapped atmosphere directly, and the results are the same. Global results from ice cores everywhere available to drill, mainly Greenland and Antarctica for the largest cores, are all consistent. Even incredibly recent layers of ice corresponding to the years of the 1960s and onwards match the direct concentration measurements that began in 1958, demonstrating their accuracy. It is, in theory, however unlikely in practice, that there is some other third variable mediating these precise correlations, something that either causes both or is caused by and then causes the other, such that it may be easier to target in our research, something that is unseeable through ice cores. It is very fortunate then that paleoclimatologists have found multiple excellent proxies for temperature. One of these proxies is pollen. I will let them explain. When pollen grains are washed or blown into bodies of water, their tough outer walls allow them to be preserved in sediment layers in the bottoms of ponds, lakes, or oceans. Because of their unique shapes, scientists can then take a core sample of the sediment layers and determine what kinds of plants were growing at the time the sediment was deposited. Knowing what types of plants were growing in the area allows scientists to make inferences about the climate at that time by using knowledge about modern and historical distributions of plants in relation to climate. By analyzing pollen from well-dated sediment cores, paleoclimatologists can obtain records of changes in vegetation going back hundreds of thousands and even millions of years. Not only can pollen records tell us about the past climate, but they can also tell us how we are impacting our climate. Comparing trends in vegetation from the last few thousand years to recent trends in vegetation can also help scientists determine whether human activities have had significant impacts on ecosystems. These pollen proxies corroborate the temperature as laid out by ice cores. Here's a library with 100 of them! Some studies corroborate other measurements up to 200,000 years. Those 100 studies can also be filtered into the reconstruction data themselves through the following. Tree rings are also excellent proxies, as their growth is massively influenced by climate. They are limited to usually a few centuries, but rarely a few millennia. Here is a resource of 85 studies relating to climate reconstruction from tree rings. And here is where to filter them into the 80 existing reconstructions. There's also speleotherms, or stalactites, stalagmites, and similar cave formations. Due to their unique formation, dripping water carrying and depositing trace minerals, they are uniquely capable of showing us periods of drought or heavy precipitation in their growth. Moreover, they also carry with them those same oxygen isotopes from earlier, solidified into their formation, which still act as proxies for temperature, precipitation again, and the volume of ice sheets. You know the drill. Here is a list of 13 studies, and no filter link is necessary because they're all reconstructions. For the sake of brevity, here's the wealth of all 2,438 climate reconstructions available here. There are reconstructions based on coral, trees, ice cores, sediment deposits, speleotherms, insects, fossils, lake beds, water levels, fires, and historical documents. They range from just a few decades or centuries ago to hundreds of thousands of years. The entire collection, with their wide range of dates and methods, all serves to definitively demonstrate the accuracy of each and every method, and to demonstrate the corroboration of one another. If there exists some variable that can account for every single reconstruction effort and every single proxy while also being wholly unrelated to both these proxies and carbon dioxide, it is near impossible to find. Indeed, given the evidence, it is impossible to conclude such a variable exists, nor is it at all a viable alternative explanation unless evidence exists for it. I came across no such evidence in my research. If anyone has any, I would be grateful to hear of it. We also have compelling evidence for the other part of our earlier prediction, ocean acidification. Since 1990, we have very accurate overall pH measures of the ocean. This is done with a variety of measurements. On the simpler end, ion-sensitive field effect transistors, or ISFETs, measure the activity of hydrogen ions in a given solution. Or we can use pH-reactive dyes, just like the pH testing strips we should all know and love from high school chemistry. These methods allow for quick estimates of specific regions, but the sensors may also be attached to ships, buoys, or floats and can get accurate readings of much larger bodies of water over a longer period of time. And per our measurements, there is a decrease. It is becoming more acidic, as predicted. We also see that, as atmospheric CO2 increases, so does seawater CO2. And there are methods available to study the ancient history of ocean acidification. To quote, "Geologists study the potential effects of acidification by digging into Earth's past when ocean carbon dioxide and temperature were similar to conditions found today. One way is to study cores, soil, and rock samples taken from the surface to deep in the Earth's crust, with layers that go back 65 million years. The chemical composition of fossils and cores from the deep ocean show that it's been 35 million years since the Earth last experienced today's high levels of atmospheric carbon dioxide. But to predict the future, what the Earth might look like at the end of the century, geologists have to look back another 20 million years. Some 55.8 million years ago, massive amounts of carbon dioxide were released into the atmosphere, and temperatures rose by about 9 degrees Fahrenheit or 5 degrees Celsius, a period known as the Paleocene-Eocene thermal maximum. Scientists don't yet know why this happened, but there are several possibilities. Intense volcanic activity, breakdown of ocean sediments, or widespread fires that burned forests, peat, and coal. Like today, the pH of the deep ocean dropped quickly as carbon dioxide rapidly rose, causing a sudden dissolution event, in which so much of the shelled sea life disappeared that the sediment changed from primarily white calcium carbonate chalk to red-brown mud. Looking even farther back, about 300 million years, geologists see a number of changes that share many of the characteristics of today's ocean acidification, including the near disappearance of coral reefs. However, no past event perfectly mimics the conditions we're seeing today. The main difference is that today, CO2 levels are rising at an unprecedented rate, even faster than during the Paleocene-Eocene thermal maximum. So that makes 2 for 2 on our predictions. I would say we've been wildly successful thus far. I will also add, fossil chemical composition is relevant as nearly all shell-building organisms use the available calcium carbonate. In the first study to demonstrate this method, they utilized a specific type of shell-building plankton. Calcium carbonate is especially susceptible to acidity, and as acidity increases, less of it is available to use. So these organisms made do by replacing calcium carbonate with borate. By analyzing the boron concentrations, we can determine how little calcium carbonate was available, and thus the ocean's acidity. Moreover, by how the concentration of boron changes over time, tells us how the acidity itself changed over time. But there's an interesting point in that last sentence quoted by the paper, that the current growth of carbon dioxide is faster than at any other measurable point, and that therefore this contemporary event is especially worrisome. Earlier, I said that the two possibilities are that this phenomenon will affect us or that it won't. Here, then, is where we can decide that. Let's start with the ocean. The onset of the Paleocene-Eocene thermal maximum, PETM, is by our best, though unfortunately far from perfect, estimates to have taken place over the course of just around 6,000 years, made through the study of sedimentation rates in oceanic cores and how they align with various astrocycles, and the disruption of those cycles apparent in the sediment. There is a wide range of other estimates, but this is the best model available at the moment, and we hope that more information will come along soon. Throughout these 6,000 years of increasing CO2 concentrations, the pH of the ocean is estimated to have decreased from 7.91 to 7.45, again known through the chemical composition of sediment on the ocean floor from the time. This may not seem like a lot, but because pH is a logarithmic scale, this ends up roughly as a 200% increase in acidity. Figuring out the range of change is easy. Every 30-odd years, the oceanic acidity increased by 1% from baseline, so not compounding. In modern times, the oceanic acidity was 8.2 on the pH scale at the dawn of the Industrial Revolution, based on powerful reconstructions, including but not limited to sediment chemistry yet again, coral reef and other shell-building animal chemistry, and knowledge of past CO2 levels. Right now, when this was written, it was 2025, and now it's 2026, the global average is 8.1. Again, the scale is logarithmic, so this ends up being a 26% increase in acidity. That means in the past 200 years, every 7.7 years, there has been a 1% increase from baseline. This is a rate of change multiple times faster than the otherwise fastest disruption to oceanic acidity ever discovered. A disruption that was so quick that organisms could not adapt, leading to mass extinction. 30 to 50% of benthic foraminifera species went extinct alone. See, when it comes to changes in these systems, as mentioned, things usually happened slowly. Things like to happen slowly on scales as large as the Earth, or even individual tiny pieces of the Earth like the oceans of the biosphere. Keep in mind, the entirety of all of Earth's water is 0.02% of its mass. Evolution, too, likes to move slowly on any scale we're familiar with. adaptation takes a lot of time. If there is an environmental change that would kill off a given species, their only response is to hope that it kills them one by one, and that successive generations develop some sort of resistance. If this change were to kill every member of that species all at once, that's it for them. And in evolutionary terms, all at once usually means on the order of a few tens of thousands of years at most. Thousands is way more than enough to cause extinctions. Hundreds is practically guaranteed. A 0.13% increase in acidity every year is not something marine life is capable of adapting to. Perhaps if it were 0.01% every year, there could be minimal casualties. We know that is not the case here and now. Ocean acidification will affect us. What about the change in global temperature from increased CO2 concentrations? Once again, we return to the PET-M, the fastest known release of CO2 into the atmosphere from antiquity. During the course of its 6,000-year start, whatever mechanism was behind it caused the ppm of atmospheric carbon dioxide to increase from a baseline of 890 to 1,980, as evidenced by seafloor sedimentation of calcium carbonate, ocean temp proxy data, and quote, simulations from an Earth system model, which includes a comprehensive carbonate system. And over this period, temperature increased by 5.6 degrees Celsius. Another quote, here we use a paleoclimate data assimilation, DA, to combine climate model and proxy information and create a spatially complete reconstruction of the PET-M and the climate state that precedes it. What proxy information specifically? Well, quote again, we incorporate 4 types of paleotemperature data into the DA. The oxygen isotopic composition, or 18O, of well-preserved glassy plankton foraminifera, the magnesium to calcium ratio of plankton foraminifera, TEX 86, the tetraether index of 86 carbons based on marine isoprenoidal glycaryl diacyl glycerol tetraethers, and MBTE5ME, the methyl branched tetraether index based on terrestrial branched GTs. Each of these temperature proxy types has an established forward model that relates the proxy units to environmental influences in a physically and statistically robust way, facilitating their use in the DA framework. Get all that? Yeah, same here. Breaking this down, we've already discussed how oxygen isotopes are proxies for temperature. The other proxies are no less fascinating. Another quote, the underlying basis for magnesium-calcium paleothermometry is that the amount of magnesium and calcite precipitated from seawater is dependent on temperature. Here we review the state of the art for the magnesium-calcium seawater paleotemperature proxy, summarized by the following. 1. Calcite, whether formed abiotically or biologically as foraminifera and ostracode shells, incorporates various amounts of magnesium into the crystal structure. 2. Uptake of magnesium varies positively with temperature. 3. The relationship between temperature and the amount of magnesium calcite has been quantified by experiments on synthetic calcite growth and by culture, core top, and sediment trap experiments using living organisms. 4. The most careful calibrations of the magnesium-calcium paleothermometer have been done for plankton foraminifera, then benthic foraminifera. There are species-specific variations in the amount of magnesium incorporated into foraminifera shells. 5. The magnesium-calcium ratio of calcite from plankton foraminifera in deep sea cores has been widely used to interpret sea surface temperatures. 6. Measurement of both magnesium-calcium and 18O in plankton foraminifera have been used to calculate 18O in seawater, and after correction for global ice volume, salinity could be inferred. 7. Imagine I have 2 extra fingers here. Magnesium-calcium from benthic foraminifera have been used to reconstruct deep sea temperatures and cooling of about 12 degrees over the last 50 million years. 8. One problem with the magnesium-calcium seawater temperature proxy is partial dissolution of foraminifera shells, which lowers the magnesium-calcium and leads to an underestimation of ocean temperature. Benthic foraminiferas appear to be more resistant to partial dissolution. 9. Past changes in the magnesium-calcium ratio of seawater are an important factor in determining the amount of magnesium in fossil skeletal calcite, and thus add another variable to the magnesium temperature proxy. All magnesium-calcium paleotemperature studies on fossil calcite older than Pleistocene should take into account the magnesium-calcium of the seawater from which it precipitated. TEX 86 is a more recent development in paleothermometers. Isn't that just such a cool word and even cooler concept? Essentially, the specific composition of specific plankton's membrane lipids is very strongly related to the temperature of the water in which it grew. So, by examining the sedimentary compositions, we can thereby derive another proxy for temperature. God, it's so cool! The last piece, MBT5ME, is the same process but applied to terrestrial membranes and serves as a proxy for air temperature, rather than sea surface temperature like Text 86. With all this data, an increase of 5.6 degrees Celsius is the only change that can account for all our findings. Thus, we determine that the rates of change are an increase of concentration by 1 part per million every 5.5 years, and a single degree Celsius increase in temperature every 1,000 years. Modern day rates of change are as follows. 2 parts per million increase every single year, a single degree Celsius increase in temperature every 24 years, 11 times faster and 42 times faster, respectively. The variance is owed to our relatively low concentrations compared to the baseline during the PETM. There are diminishing returns as concentrations increase, thus rendering each additional ppm slightly less effective at raising the temperature than the last. We are nevertheless rapidly outpacing this mass extinction event in the very cause of death. We can be sure that this change, whatever is causing it, will affect us. As before, we can make predictions about what these changes will be. Obviously, increasing temperatures and increasing oceanic acidity. Also, with warming temperatures, we expect glaciers and ice sheets to lose mass, and that subsequent meltwater to raise sea level. For the lowered pH, we can expect vast ecological impacts on species that are susceptible to it. We may also expect worsened droughts and drier conditions as the heat of some areas drives away rain and humidity. These predictions, and other effects thereof, will be the subject matter of Act 3. Class dismissed.